So welcome to Spectral Processing Basics, powered by NeverEngine Labs. My name is Gustav Scholda, as you probably already know, and we will talk about what kind of data is actually inside when you do a spectral analysis. What kind of data do you get out, and what can you do with it before you resynthesize the data? So let's start with the sum of signs, the basic principle of this. Just blowing up my phone, okay. So let's start with the sum of signs. Basically, you're sending audio into the analysis. Then you get an array of amplitudes and frequencies for each sinusoid, or sine wave actually. And then you put that array into the resynthesis, which is usually an oscillator bank, and you get audio out. But if you look at that in schema, looking at this wire here, that's the reason actually why P. Johnston called this the wire between, because it's just an ordinary stereo wire. You don't see any parallel wires going from the spectral analysis to the oscillator bank. So how do they do that? Actually, we need to transfer, like if you do a 256 partial analysis, you need to transfer 256 individual amplitudes and frequency data to the oscillator bank. And they do it in a single stereo wire. So there has to be some other technique than parallel transmission. So we'll just open up this sound here. That's actually the same sound as we had before. I just placed an oscilloscope inside this wire to see what's going on in there. Just keep looking. Is it okay for everybody? I just want to double check before I go on. There might be some sort of delay as well. I just want to make sure that everybody can... Okay, seems to work great. Okay, nice. So I placed this oscilloscope inside this stereo wire to see what's going on. If we play that sound, so what we see here is the left channel and the right channel of that stereo wire, and you probably already know that the left channel transfers the amplitudes and the right channel transfers the frequencies. So in this case, I'm still having serial data, not parallel data, like I would expect in an array, right? So what you see here is amplitude 1. I'll just zoom in twice. So this is one frame. We will see that better in my presentation. I'll just go over there. So a frame actually is an array of data. So what we see is a stream of amplitudes. I'm discussing the amplitudes now. For the frequencies, it's exactly the same. We see a stream of amplitudes going in time, and if we divide that into frames, like usually there are much more than 6 sample frames. Usually the analysis is doing like 256, but for simplicity we will do 6 samples. So if I divide that into, if I think of that as framed data, I would just divide it into 6 sample frames. Again, 6 samples just because we are assuming this is a 6 partial analysis or something, right? So these are the frames, and these actually that's actually the same as you would do in CopyTalk if you do an array and do 1 to 6 collect e a value suffix to e. Then each value would, this would be value 1, 2, 3, 4, 5, 6, and then it will again be value 1, 2, 3, 4, 5, 6, and so on. And the update speed would be 6 samples. So what's happening in this stream of amplitudes is that they are actually transmitting this parallel data as serial data. That's the reason why they do it in frames. So if we look at this stream of amplitudes again, is this really the time axis we are looking at? Or should we rather put this, if we take frame 1, 2, 3, 4 and put this right behind each other? Actually, that's the time axis, and these are just samples. It's very, might be very difficult to grasp at the first moment. Okay. But actually what we hear, the time axis, is actually in the z-axis. So we are getting this stream of amplitudes, and if we take frame 1 and put it here, frame 2 and put it here, this is actually like time is moving. So value 1, like amplitude 1, will move in time like this. It will have a value of something like 0.8 here, and then it will have 0.6 and 0.3 and 1.0 or something. So don't get confused by this concept. What we hear in the spectral analysis is actually the parallel data we are getting from the spectral analysis. We are getting the amplitude and the frequency for each sine wave. It's updated every like 256 samples or 6 samples if we go back here. So this, assuming this would be amplitude 1, this would be updated every 6 samples. We get a new amplitude for sine oscillator 1, for example. Just want to make sure, is there any question about this concept? Because it's very important that you get this time and samples concept, and that actually this data is transmitted in frames which are actually the same as an array. I hope everybody gets it. If not, please ask your question now. I'm just waiting a little because there could be a delay. It's great that we can edit the video afterwards. I can cut out the pauses. Okay. That's very good, because that's actually the most difficult part to get. That, because usually in the time domain we would look at samples, and this would be the sample domain and the time domain would be the same, but not if we transfer data in frames. So let's look at another sound I made here. So we can look at these frames. That's again a sample, so I can let this run. Okay, so if I set this to manual, I can go through that spectral data frame by frame, and that's actually that's exactly what's happening if you're doing freezing. Then you're just sticking onto one frame. That's exactly what we have here. Notice that a single frame actually sounds very synthetic and not at all like the original sample. We can even step through that frame by frame, so you can see. Have a look at the amplitudes. For the frequencies, it's not that easy to see any difference, but if you look at the amplitudes, you can see what is changing frame by frame. I'll do that now. Okay. Another way to visualize the whole thing would be to put the tempo way down. If I change the rate, I'm sorry, I should mute when I speak. If I change the rate to something more extreme, like 100, then 100 times slower, you will see what I mean again. So this is just a visualization of what happens if you change the rate of your time index, for example. So you see that those amplitudes are changing very slow, and that's also the reason why if you put the rate really down, you would get those synthetic effects, because there is no change in the sound, or there is change but it's very slow. So you get this very synthetic character. That was just another way to demonstrate these frames. So, okay, so we want to... Oh, can you explain a bit more about what a frame is? Yeah, as I said here, I'm going back. This is a stream of amplitudes. This is just a stream of values, actually. But if I know this is frame data, I can divide that into the frame size, which in this case I chose 6 samples. And a frame equals to an array. So imagine you're doing this kind of array here. Then you get 6 values, and you can change them and they run in parallel. And that's exactly what's happening here. So you have to imagine that they run in parallel, but they are transferred in serial. That's exactly what I wanted to show here. So if you take each frame and then put it onto the z-axis, actually, then you get this concept of the time is moving actually from the first amplitude. It will move to this value, to this value, and to this value. And the second for the second amplitude, it's the same. It will move from this value to this value, to this value, and to this value. So this is an array, and at the same time, a frame. I hope that was clear enough. By the way, you can assume those frames if you're looking into your Oh, there is no analysis going on here. If you look at the lowest analyzed FRAC, that's the setting for how many partials you're going to analyze, or on how many partials you're going to analyze your sound. And this is exactly the same setting that is determining defining the frame length. So if you choose above 2F, this equals to 256 partials. If you take above 1F, this will be 512. So the only thing you have to remember is that the first setting is 512 samples frame and also 512 partials. And then you just divide it by 2. So the second setting is 256, 128, 64, and 32. Of course, you should usually set that to so it fits with the sample you are analyzing. So this lowest analyzed FRAC exactly makes sense. You don't gain anything if you analyze something that has no frequencies above 173 Hertz and you analyze it with 512 partials. You won't gain anything. So usually you should set that so it fits with your sample you're going to analyze. Okay, so now we know how this spectral data, how it works, how it's presented in Kima. Maybe I should note that for the frequencies, the concept of frames is exactly the same, but the values are different because they're transferring a value which has to be multiplied by a signal processor half sample rate. So if you're working on 48 kilohertz, for example, then you need to multiply that value by 24,000 to get the real frequency value. This is just the scaling. This is just the scaling actually, and it's just done so you can transfer that data because you, as you know, you in the wires between modules you can't transfer any data which exceeds plus or minus 1. So they are just scaling that by signal processor half sample rate. And that's also the reason sorry, why you maybe let's take this example again. It's muted, so don't worry if you don't hear anything. That's also the reason, I hope you can see that line actually on the video, why this is going up. It looks like a sawtooth or something, like a reversed one. So those values are determining the frequency. So if you look here, this is the fundamental, or maybe there's a kick drum right now. So this the amplitude one is really high, and the frequency, I can't see it myself here. It's a very low value. So if you would multiply that value by signal processor half sample rate, you would get the according frequency value to that amplitude. Okay, so now that we know how the data is transmitted from the analyzers to the resynthesis, how can we manipulate that data? So the initial thought would be to bring them back to parallel, because that's actually the way they are meant to. So if we do the serial to parallel, we could, for example, sample and hold the first value, again considering in this case amplitudes, but you would do the same for frequencies. So if we sample and hold the first value, we would get a stream which is which is exactly what the first like the first index of this array, or the amplitude one, is doing. So this is the amplitudes of sine oscillator 1. If you sample and hold that, then you will get again time and samples in the same domain. So the only thing we have to do now is we need to interpolate those values so you don't get any clicks, because then the sudden changes would of course result in clicks. So if you do that, I'm doing this here with a replicator. Maybe some of you have read my blog post about individual oscillator resynthesis. This is exactly that. So what I'm doing is I'm sample and holding for 256 samples. I'm sample and holding the voice number -1 means, so for the first voice will have no offset, so this will be actually the sample number 1, or the amplitude number 1, or the index 1, whatever you prefer. And if I sample and hold that value and then interpolate that, I'm doing that with a gain module, because that interpolates at sample rate, and I feed that into a single sine oscillator. You can see here that I did exactly that what I was talking about before. I'm multiplying the fracs, or the frequencies, by signal processor half sample rate, and for the envelope I'll use that the output of that gain module. So, and using this replication, I'm doing this for 256 times, so this part will be done 256 times, and I can listen to that too. It takes some time. Okay. So we see that works, but maybe I should have let that run. If you look at the DSP usage, I'm running a Pacarana here, and it's, you know, it's nearly full. So this is obviously not the most efficient way to do it. Whoop. Where's schema again? Here it is. No. So this is obviously not the most efficient way to do it. God. Okay. Although we could do some funky stuff in here, you could place delays in there, or any kind of processing you would like, and it would be this kind of processing would run on every single oscillator. This is something you can't do with the oscillator bank. But as I already said, it's not very efficient. So we have to think about a way to manipulate that data, which is presented in serial serial data. We have to manipulate that. So a very easy example of this is just multiplying again this stream of amplitudes here with the 6 sample frame, and we got 4 frames here presented. And if I multiply that with a pulse train, which is only 1 sample long, and 0 for the other ones, what would I get? Of course I would get the very first value of each frame of each array, whatever you prefer. So that's the reason why we have to do all that manipulations have to be done at sample rate. Because if I would do that multiplication, if I would do that not at sample rate, I wouldn't be able to generate a 1 sample trigger. So this would smear out if this would be a curve that's going like in a triangle shape down, then I wouldn't get the very first one. I would also get some values of the other ones too. So that's actually the reason why the whole manipulation of that spectral data stream has to be at sample rate. I hope that's clear for everybody. I'll just wait a little and see for your reactions, because this is the second really important thing to grasp, that it's not possible to manipulate that data with copy talk. because CopyTalk is only updating every millisecond, and every millisecond is not sample rate, so it just wouldn't work. So I'm just waiting a little for questions. Okay, it seems to work. That's great. I assumed that there will be more questions about this. At least for me, it took some time to get that. Okay. So, let's start doing that. If you look at this sound, so this is just our player, you know this part already. I'm splitting it up into amplitudes and frequencies. By the way, those modules here, we just made them for visual feedback. So you can also use a left channel only and right channel only. You can also use the channeler module, but it's much better to visualize if you have an A for amplitudes and a F for frequencies. So what I'm doing here is I'm using a product because that works at sample rate. I need to use a module to calculate the product. If I would do it in CopyTalk, it would just update every milliseconds and it wouldn't work. And the other thing I'm doing is quite similar to this example here. I'm doing a pulse train, and the pulse train has the exact same period as my frame length, which is 256 samples, and I can change the duty cycle of this pulse train. Okay, so what's happening if I multiply? What's actually happening is here it is shown for only the first value, but what we get here with this pulse train would be a low pass, a spectral low pass. Let's look at that and listen to that. Okay. Here I can change the duty cycle, so you might pay attention to what I'm doing here and also what's happening here to the amplitudes. See, now they're all gone, so I'm actually killing everything. Now I only have the very first one. Okay. So that's a way to do some EQing in the spectral domain. Is there any questions? Any question about this? Then feel free to ask. Otherwise, I'll continue on how you can generate other control signals. Or it might be interesting to take a look at how that pulse train is looking. Okay, calling that pulse train. Whoop. Oh, where is it now? Okay. Lost in monitors. Ah, it's up there. Sorry for that. Okay. make that smaller. Okay. So what you see on the left side is that pulse train. So changing the duty cycle, as you see here, as expected. And that's the signal I'm multiplying with the amplitudes. So it's actually very easy. You can do the inverse of this and you get a spectral high pass, for example. Or you could combine two pulse trains and get a spectral band pass, for example. Okay, questions will come later. Okay, fine. So, okay, the pulse trains are a nice way to manipulate that data, but the very obvious one is the synthetic spectrum from array. Because what the synthetic spectrum from array does is I can define an array and it will output that as spectral data. That's exactly what we need. So you probably have already looked into the spectral control signals schema file in the SpectralLab. So there are a lot of these. This one is the 16 faders. So I'm not going into details about the Capitalog I'm using here because I guess you're familiar with how to make arrays. Or if not, we can discuss that in the end. So what I'm doing is I'm generating a synthetic spectrum of frame length. I'm defining that here in the script because it's just more practical. And these 16 faders get multiplied by my amplitude. So these 16 faders are just values. We can see that in the oscilloscope display. You can see that if I move fader 1, fader 2, so what you see here is the control signal I'm generating. I'm multiplying this signal with the amplitudes. So all amplitudes multiplied by 0 will get killed, and all the other ones I can scale them. So this is another way to EQ. I made those faders in a way that I don't want to end up with 256 faders. This would be sort of impractical. So I grouped the first 12 faders are really for the very first for the first 12 partials, and up starting from fader 13 I'm starting to group partials together. So this is what you can hear, and you can also see that here. So this is the control signal now I'm generating. And I can start to randomize that, except of the master fader. And you get some from pretty wild to subtle spectral EQing. And this is just done by multiplying that control signal I'm getting from the synthetic spectrum from array with the amplitudes. So if you know how to do it, it's not really complicated at all. You're just generating those arrays using a synthetic spectrum from array, and then you start to multiply that with your amplitudes, for example. Okay. So, to do an EQ really, we can actually use the product one. Is might be a better way to use, because the product one is multiplying by it can multiply by more than one, and also the multiplication, that the scaling is based on an exponential scale. So this is really fitting for amplitudes and frequencies, because if you scale something by 0.5, you will do minus 6 dB, and if you scale something by 2, you will do plus 6 dB. And the way the product 1 works is, if you set the order to 1, this would correspond to 6 dB. You can see that here in the product 1 description, there is the order, and you can see that a setting of 1 would be plus minus 6 dB. So then you get those 16 faders, and if you move the fader fully up, it will be plus 6 dB. If you move it fully down, it will be minus 6 dB. So this, and also if you do it for the order 4, this would be plus minus 24 dB, which I'll do right now, and that sounds really better than just scaling them linearly. So this is the product 1 much more reflects on how we perceive sound. Below here you will see the control signal I'm generating using those faders. Okay, you already have those sounds in the SpectralLab, so you can experiment with them on your own. And also I wanted to say that's also the reason why most of the modules of the SPCSR are having a sound input for, in this case for the multiplier, but for the Foreman shifter it will be a Foreman shift input, or for the exponential smoother it's a smoothing input. It has to be a sound, because it has to work at sample rate. Again, think about it. To do that, we have to do the calculation. We have to do the calculation at sample rate. We can generate the array with Capitalk. So this is actually the perfect connection between sample rate processing and Capitalk usage to generate control signals. Maybe let's take another example. So again, I'm having the 16 faders here to do some EQ on the amplitudes, and I'm using the product 1 on the frequencies. I'm using an order 1 here, which results into plus minus an octave. And here I'm presenting you another way to generate sample rate control signals, which is using the Xen oscillator. The Xen oscillator is another way to do that, and you can use Capitalk inside, but it will generate a sample accurate control signal. So it's actually very simple. I'm just having two x values and two y values I can move, and if I move them all together, it will be a usual pitch shift. But I can also send you will see it in the oscilloscope display. This is the Xen. It's much easier if you. So this is my 2-point control signal. I'm having x1, x2, y1 and y2. You can name them whatever you prefer, but it's just convenient to use it like that. So if I set x on the x-axis, I'm specifying where in the spectrum I'm doing my y value. You will see that if I do that to -1 and 1, the y1 will affect the very first frequency in this case, because I'm using that on the frequencies, and y2 will be for the very last one. So If I raise y1 and between those it will get interpolated. I think I'll just show that. So if I don't make this line straight, what's happening is that I'm pitch shifting the lower values, or the lower indexes, or the lower partials, different from the higher partials. And I'm doing this with those two values, and the Xen oscillator is able to interpolate between those. I'm able to pitch shift the lower partials, and then doing less and less and less and less pitch shift until I reach the highest partial, where I do no pitch shift now. We can do it the other way around too. We can start to pitch shift the higher partials and not pitch shift the low partials. If I set this 1 to 0 here. And if I move them both, then I get a usual pitch shift, you know. If I'll just move both to pitch the whole thing an octave down, for example. And you can draw arbitrary curves with that, and you can even use more of this. Right now I'm using only 2 points to define the line, but you can use more of them, of course. For example, in this curve we just saw is I'm pitching the lower partials down while at the same time pitching the higher partials up. Okay. So maybe let's open that spectral control. Where is it? Here we are, spectral control prototypes. So those are all the prototypes we have so far. Those are all based on the Xen oscillator or the synthetic spectrum from Array. And please feel free to make your own. Here's a template you can use for your own creations if you haven't done yet. And you can use those spectral control signals in any of the SPCSR modules, or you can even develop your own algorithms and use them there. For example, if we go to this sound here with the smoothing and freezing, just to show another SPCSR module. For example, here we have an exponential smoother. Just make that a little bigger. Okay. We have an exponential smoother, and the input for smoothing is, as I said before. Thanks, Louis. Yeah, I think so too. Pitch shifting frequency bands is very cool. Yeah. So it has an audio input where you can send your control data in. So you're able to not only smooth the amplitudes, you can also smooth only the lower partials or the higher partials or whatever you prefer. So in this case, in this sound here, we are having a single fader. So this is, and we can define a bandwidth. So let's look at the control signal. If we play the sound, it will all come clear. As you can probably hear, this control signal is slowly going through the spectrum, and the bandwidth is determining how many partials are, in this case, freezed at the same time. So if you drive the smooth to a 1, it will freeze. So this is exactly what's happening here. If I make the bandwidth really high, you will easily hear that smoothing effect, but it's actually drifting through the spectrum because I made my control signal in a way that it will wrap around and go in circles. So if you set the bandwidth high enough, you can hear the effect really well. And you can also do that for the Foreman shifting. That's what I did for the voice transformations. With all the knowledge we now have, it might be easier to look at the sound. So what I'm having here is I'm using a Foreman shifter on the amplitudes, of course, and the Foreman shift input also works at sample rate. So I can the same thing I did before with the pitch shifting, where I shifted the lower partials but didn't affect the higher partials. I can do also with the Foremans. So I can start to move for the lower partials, I'll move the Foremans down, and for another group I will move them up, and so on. And at the same time I'm doing that for the pitch. And also I'm using a noise and the product 1. Remember, we used the product 1 for the amps like an EQ, so the noise will do some random EQing of the amplitudes, which results in a rough voice actually. So if I play that sound, it might be more clear than before what we're actually doing here. Oh, is it searching for some sample?
Why,
no.
I take good care of my Macintosh computer.
So what you see here is, here we have the Foremans. I made 4 groups, and you can define the crossover partial. And the same applies to the pitches. And now you can start to, for the pitch shifting, for example, it's actually very similar to what we did before with those 2 points, but now we have 4 groups. So we can start to pitch shift from the very first partial up to the 5th, and that's what the P1 fader is controlling.
Because it broods under its hood like a perched falcon. Because it jumps like a skittish horse, and sometimes throws me. Because it is pokey when cold. Because plastic is a sad, strong material that is charming.
And also we can do that for the Foremans.
Because it is flighty. Because my mind flies into it through my fingers. Because it leaps forward and backward, is an endless sniffer and searcher. Because its keys click like hail on a rock, and it winks when it goes out.
It puts word heaps in hordes for me, dozens of pockets of gold under boulders and stream beds, identical seed pods.
And don't forget the noise function, which is also very nice.
Because whole worlds of writing can be boldly laid out and then highlighted and vanish in a flash at delete, so it teaches of impermanence and pain.
This is something for future updates. Right now the noise is actually applied to the whole spectrum, but it would be quite easy to use something like the Xenon oscillator we had before with those 2 points. We could multiply that by the noise, and so we could define how much noise we are feeding for the lower partials and for the higher partials. This could be a nice improvement for that sound. Okay. So far, so good. I'm awaiting your questions now, actually. Because Yeah. Or you can just tell me that I should show some more of that sound or whatever you prefer. Just waiting a little for you to catch up for the delay. Ah, it seems like the delay is not too bad. Someone's typing already. Feel free to ask whatever you want, you know? Now it's the time. Yeah, Louis, you're right, actually. The tracks 3 is very similar to what we are doing here with the formant shifting and pitch shifting, and you could also use something like those 4 groups we had here, where I'm defining 4 groups. You can also use that on the noise, so you can even define 4 different groups on how much you inject noise into partials. And yeah, that's a large field for experimentation, voice processing. By smoothing a partial. Okay. If you do, let's make that very simple. Okay, let's start with a constant. This will be some input value. And I'm using a delay on that. That's actually the way Pete did it, did the smoothing in the very first place. So I can call that feedback smooth, and that scale 1 minus smooth. Set that pre-0 and have a sound to global controller. Okay, I'll just call it out. Okay. Just need to scale it. Okay, this will be from 0 to 1. Okay, so if I set smooth to 0, this is an explanation for exponential smoothing. It will become clear, I guess. What smoothing is I'm changing the rate of change. So if a value starts from 0.5 and goes down to 0.3, and if I smooth that, it will be interpolated between those values. If I smooth that a lot, or with one sample, it's maybe not enough. That's too fast. Okay, with one sample it's too fast. But we can also demonstrate that with... Forget about the delay. The copy talk message smooth is exactly what we are doing. I'm specifying a smooth time here, zooming that in so you can see that. So if I have a smooth time of 0.5 seconds, any change I will do, it will take 0.5 seconds to reach the new value. You see, if I move the value, the out value will go to that, but it will take some time. And that's exactly what we are doing with the partials. So think about it like this: if you smooth the amplitudes of the spectrum, the changes in the changes will be slower. Or even if you think about an amplitude would go wiggle wiggle around a certain value like this, as you can see here, the out value doesn't change at all, or very not as much as the input value is changing. Maybe we can have a look at that inside the spectrum too. Yeah, why not with that one? And I'm taking a... Okay. There are different types of smoothing. I think they are quite well documented in there. But if you have some specific questions afterwards, feel free. So I'm just using a constant now, so I'm smoothing all partials. Okay. Where's my... Here is my smooth value. I will put that up. Okay. So if I don't smooth and play that, if you look at those amplitudes, they change quite fast and wiggle around. And if I start to smooth, I will smooth out those changes. It sounds a little bit like a reverb. And if I set smooth to 1, I will freeze. But I think you can see very clear as I move smooth down, you see a lot of small movements, and if I move that up, it all gets smoothed out. But again, this smoothing is done. Where is it? Yeah, maybe this graphic here demonstrates it quite well. I'm not smoothing the whole stream of amplitudes. I'm smoothing really the changes for each individual partial. Right? That's important. Oh, there are some messages. Oop, I just have to read that. Between partial and formant. Okay, I will do that next. We can also smooth the frequencies. Right now I smooth the amplitudes, but we can also smooth the frequencies. I will do that right now. No, not just using the smooth message makes smoothing happen. It's the module that makes smoothing happen. Okay, let's try because there was the question was from Lasse was not the frequencies directly. We can do that for the frequencies as well. Right now I smooth the amplitudes, but I can also smooth the frequencies. Do it like that. And then change that here. These are the fracs, these are the amplitudes. Okay, very same thing, but I'm smoothing the frequencies. So I'm smoothing out the changes for the frequencies. This will be quite vocoder-like. For drum loops, it's not that audible actually. You hear that the frequencies are very static, but if we do that for a voice sample, then you will hear it will be very vocoder-like. Let's see if we can... Oh, that's a complicated Capitalk stuff here, so I will not change that right now. No, but if you do it for the voice, it will it will be very vocoding-like. Okay, verlang to yeah, I hope Carla will do that. Yes, Christian is right. It's effectively a low-pass filter at audio rate, but with the difference that I'm not using that low-pass filter on the whole stream. I'm using that low-pass filter for each partial directly, individually. Sorry. So there was one other question about the difference between formants and partials. Yes, so something was there. I lost it. Is that still a question I should answer? Yes, I agree, Marinos. The smoothers will do even more crazy things if we were able to make bigger windows and go a little deeper into the analysis part. Oh yeah, there was this question about quickly the difference between partial and formant. So the formants are the spectral envelope. So if you look at the spectrum, like, let's demonstrate that very short, because please don't confuse those two words to be the same. If I do an analysis of Carla's, I guess that's the right one. No, it was the other way around, because you can see them quite clear. Yeah. So let's take an oscilloscope display and an oscillator bank. And do that for, I think it was 128 partials here, and we'll just look at the amplitudes now, because those determine the spectral envelope. What do you see here? I'll just zoom a little more in. The shape of the spectrum, that's the formants. So we see there's the fundamental here, there's a formant, and here we see a little formant, and here's another formant. Okay, so this is if you were to low pass that, or if you were to smooth that stream of values, you would get a spectral envelope, and this is what we call the formants. If we shift the formants, we are basically taking the spectral envelope and shifting it up or down. The important thing is that we, with the formant shifter in the SPCSR, we can do that for parts of the spectrum. So if that part of the spectrum contains a strong formant and we shift that down, it will be lower in pitch. And the partial is just a single partial, it's just a single index value here. The formants are more about the spectral shape or the spectral envelope. Okay. Yes. In general, the formant is an envelope of where the energy lies in the partials. Yeah, I agree. A bit on formants. Yeah, I just explained that. Maybe there are some other questions, like specific ones or on specific modules, or while I'm waiting, I'm thinking about the next tutorial will be about how we can write those algorithms on your own. Like what does the formant shifter, if you look inside that module, what does the bit shifting do if you look inside that module, so that some of you will be able to develop your own sample rate processing, spectral manipulating modules. Might be a nice way as a spectral processing pro tutorial or something like that. I'm just typing here, feel free to ask. Now it's the time, because it's probably quicker. Yeah, I guess so. It gets quite yeah, complicated if you want to do that, but I think it would be perfect for the next tutorial. That's nice, Marinas. Okay. If there are no more questions, I would close the session. Okay, great. Just waiting a little. Yes. Okay, seems all people seem to be fine. So, thank you for participating in this. If you have any questions, feel free to ask them in the SpectralLab or just message me directly. But probably using the SpectralLab channel would be nice, so everybody can read what we are talking about. And use the Slack. It's definitely worth it, and we can discuss there, we can share sounds there, so yeah, just do it. So have a good night. Bye.